I'd like to thank the SAS for the opportunity to share a platform with the illustrious Piers Corbyn, whose groundbreaking work shows that our climate is dependent on what's happening on the Sun. Now, in this talk, I want to explore how and why that might be happening. The first thing to remember is that space is not a vacuum through which only radiation can pass, as scientists in the early 20th century thought. We now know that space is filled with plasma. The second thing is that the atmosphere is not an electrical insulator, as it's often thought to be. Recently, it's been recognized that the atmosphere is also a weak plasma, so it's plasma all the way down from the Sun to the air we're breathing in this room. This gives us a whole new understanding of the way the Earth is connected to the Sun. We are directly connected via plasma, and I believe that this can explain why many of the climate effects move in sync with the Sun's activity. And because plasma is such a fundamentally different medium to solids, liquids and gases that we're more familiar with, I'd like to spend a couple of minutes explaining what plasma is and why it's so important. So plasma is often called an ionized gas, and that's true, but it doesn't really convey the sense of just how different to a normal gas plasma is. And the difference is due to the ionization. An atom consists of a number of electrons orbiting a nucleus of protons and neutrons. And the number of electrons equals the number of protons in the nucleus, so an atom is electrically neutral, and this means it can't really feel electromagnetic forces. In a plasma, some of the atoms are ionized. Some electrons are separated from their nuclei and are able to move independently. And this means that the gas can now respond to electromagnetic forces. And only a small percentage of atoms in the gas need to be ionized in order to make it behave as a plasma. It's called plasma because it's so lifelike. For example, it can form cells and filaments, and it responds to changes in very complex ways. And this behavior is so different to normal gases that plasma is now recognized as being a fourth state of matter. At the level of the individual electron or positive nucleus, the electromagnetic fields in the rest of the plasma cause each particle to move. And the particle's own electrostatic field moves with it, and any moving charge creates a magnetic field. Together, these change the fields in the plasma in the particle's immediate neighborhood, to which other particles respond. So therefore, there's a feedback loop between the fields and the motions of the particles, and this results in the complex collective behavior. Now, a plasma can conduct electricity because some of the positive and negative charges have been separated. And another property of a plasma is that it can be magnetized. Under the right conditions, it can carry magnetic energy embedded within itself, rather like a permanent magnet carries its magnetic field with it. And a third property of plasma is due to Faraday's law of induction, which says that any change in a magnetic field induces a voltage, which will cause a current, and Lenz's law says that the current will try to maintain the original magnetic field. So, for example, if a magnetized plasma has to flow around an object, the fields change, and currents will arise in the plasma to try to oppose that change. The plasma has been studied for over a century now, and scientists know an awful lot more about it than the few things I've mentioned. But I hope you've got a sense of how it behaves and why it does so. So we'll now move on to the main part of the presentation. We'll start by looking at the variability of the Sun's output. And then we'll look at the Sun-Earth connection mechanisms, which explain how the Sun's output reaches the Earth's upper atmosphere via the plasma in space, and how the Sun's variable magnetic field affects the arrival rate of galactic cosmic rays. In the third section, we'll explore the ways in which the effects in the Earth's upper atmosphere are transmitted to the lower atmosphere and affect the global electric circuit. And I'll finish with some comments about climate systems which look remarkably similar to the known plasma effects in the upper atmosphere. So, to start with our variable sun. It's often claimed that the sun's output is almost constant because the total irradiance only varies by around 0.1% over the course of an 11-year solar sunspot cycle. But this overlooks the fact that the radiation in some parts of the spectrum varies over a much larger range, and it also ignores the fact that radiation is not the only output from the sun. The sun's radiation is like that from a black body. The peak radiation measured above the Earth's atmosphere is consistent with a black body at around 5800 K at the sun. And this is assumed to be the temperature of the photosphere from where most of the radiation is emitted. There is some radiation at all wavelengths from X-rays to radio, but most is within the UV to IR range. Now, whilst the total radiant output is reasonably constant during the 11-year solar cycle, the UV component varies significantly. Woods and Rotman 2002 found that during solar cycle 22, longer UV wavelengths varied by 15%, mid-length UV between 15 and 70%, and extreme UV by 150 to 700%. Now, although the power radiated in UV is small compared to the total irradiance, we'll see later that the effects of UV on Earth are disproportionate to the power level. Therefore, the claim that the total solar irradiance variation is negligible is missing an important point when it comes to possible climate effects. As I mentioned, radiation is not the only output from the sun. Sunspots are an indication of the magnetic activity of the sun, and the study of sunspot numbers first led scientists to the recognition of the 11-year Schwabe cycle. The sun's dipole magnetic field reverses every 11 years, at the time of solar maximum, when sunspots are most numerous. During one cycle, the magnetic field is orientated approximately parallel with the rotation axis at solar minimum. As solar maximum approaches, the field decays, starts to turn over, and re-emerges anti-parallel with the rotation axis, somewhat like inversion of a bar magnet inside the sun. The strength of the magnetic field varies in sync with the sunspot cycle. During a typical 11-year cycle, the field strength varies from around 5 to 8 nanoteslas. That's a 66% increase. And since 1880, the sun's field strength has ranged between 2 and 9.5 nanoteslas. The variation in field strength appears to be connected with the amount of magnetic flux flowing away from polar regions on so-called open field lines. That is, the magnetic field lines which don't loop back into the sun, but stretch out into the heliosphere and form the interplanetary magnetic field, or IMF. And this open flux ranges from around 2 to 8 times 10 to the 14 Webers, and it's carried by the solar wind. The solar wind is another output from the sun. It consists mainly of plasma in the form of protons and electrons, plus a small proportion of helium nuclei. The solar wind is emitted at huge velocities. The so-called slow wind comes from the equatorial regions and has a velocity of up to 450 kilometers a second. The fast wind is emitted along the open field lines from the polar regions and has a typical velocity of around 800 kilometers a second, but it can be up to 1,000 kilometers a second. And the solar wind velocity varies with the magnetic field strength over the solar cycle. Wang and Sheely, 2013, reported that the solar wind mass flux, proton density, and energy density in the corona also vary over a range of more than 2 orders of magnitude in sync with the magnetic field strength of the open field lines. Longer-term cycles in solar activity also occur, and here's a list of major cycles identified in various records. Geomagnetic data has been recorded since the mid-19th century. The continuous sunspot count record extends back to the 17th century, and some records go back to the 13th. And both data types are indications of the magnetic activity on the Sun, which we can now relate to other outputs using modern measurements. The record of cosmogenic isotopes, such as beryllium-10 in ice cores and carbon-14 in tree rings and marine sediments, can be used as proxies for solar activity going back thousands of years. All the records show that the cycle lengths are not constant. These figures are just averages. Now, the amplitude of these oscillations are indications of the long-term changes in the Sun's output. And here are just a few examples from the literature. Magnetic activity more than doubled between 1901 and 1995. Mid-UV increased by around 50% over the last 400 years. Solar activity during the Gleisberg cycle 1540 to 1645 was around 25% of the modern era. Average open solar flux during the Maunder minimum was only 11% of its peak value during the recent grand solar maximum. And the average swab cycle length was 14 years during the low solar activity of the Maunder minimum, compared to just 9 years at the start of the medieval warm period. So I think these examples demonstrate the long-term variability of the Sun, on which the Schwab cycle variations are overlaid. Let's look now at some very short-term variations. The Sun is a highly dynamic place. We've known for years that there are occasional outbursts of radiation from regions of exceptionally strong magnetic field, and these regions suddenly flare up. The radiation from these solar flares often includes X-rays and extreme UV, and one of the strongest flares so far recorded is known as the Carrington event of 1859. Now, solar flares often occur with another type of emission known as a coronal mass ejection, or CME, in which millions of tons of hot plasma are ejected from the surface. We now know that if a CME heads towards Earth, it affects the Earth's own magnetic field and causes very bright auroras and magnetic storms. Another form of eruption is known as a solar proton event, which, as its name suggests, generates huge quantities of protons flowing away from the Sun. These are often, but not always, associated with flare activity and CMEs. Now, all these solar eruptions involve conversion of part of the Sun's magnetic energy into one or more of these phenomena. The variability of the Sun has another important effect involving galactic cosmic rays. These are generated by a variety of high-energy events in our galaxy, including supernovae. And variations in the Sun's magnetic field strength are known to alter the number of galactic cosmic rays reaching the Earth. Varenholt and Looning, 2013, described the effect. The Sun's magnetic field has a profound impact on cosmic rays. When the magnetic field is strong, it shields the Earth. When it's weak, cosmic rays easily penetrate deep into the Earth's atmosphere in increased quantities. The result is that cosmic rays are the main source of ionization in the troposphere and lower stratosphere. And we'll see how important this is later. The cosmic ray flux varies by 10 to 15% over the solar cycle. That's 100 to 150 times more than the variation in total solar irradiance. The average CR flux has declined considerably over the last 150 years, but has been increasing again since the beginning of the 21st century. And the cosmic ray flux has also varied over the long term. Over 11,500 years, repeated cold spells coincided with times of high cosmic ray influx, according to Svensmark 2013. Changes in the CR flux correlate with a medieval warm period, the Little Ice Age, and the modern warm period of the 20th century. So to summarise part one, we've seen that the Sun is a highly variable star, despite claims to the contrary from some quarters. As Eddy, 1976, wondered, why we think the Sun should be perfect, constant and regular when other stars are not, is more a question for social than for physical science. Remember especially that the solar wind plasma and magnetic field vary very significantly. The next question is, how does that change conditions near the Earth? So in part two of the talk, we'll look at how the Sun affects the upper layers of the Earth's atmosphere. And we'll start by looking at the environment around the Sun. The heliosphere is a magnetic bubble around the Sun formed by the solar wind, in which the Sun's magnetic field dominates the fields from the rest of the galaxy. Its radius is over 3 times the radius of Neptune's orbit. The interplanetary magnetic field, or IMF, within the heliosphere is carried away from the Sun by the solar wind plasma, which tends to follow the field lines which are already present. Near the poles, the field lines are open to the heliosphere, and as we get further from the Sun, the field lines and the solar wind curve down to the equatorial plane. The oppositely directed field lines above and below the equatorial plane imply that there's an electric current in a sheet in that plane. And this heliospheric current sheet, or HCS, separates the north and south polarities of the IMF. In plan view, the Sun's rotation generates a spiral pattern in the IMF. This is called the Parker spiral. Near solar maximum, the Sun's dipole field becomes more convoluted, and the dividing line between north and south polarities adopts the shape of the seam on a tennis ball. And so the HCS also becomes wavy, and it's often described as a twirling ballerina's skirt, as you can see on the right. The Earth is sometimes above and sometimes below the skirt, passing through the current sheet as it moves from one side to the other into regions with opposite polarity. The Earth's magnetic field produces a similar but much smaller magnetic bubble called the magnetosphere, where the Earth's magnetic field interacts with the solar wind. The magnetosphere is an obstacle to the flow of the magnetized solar wind. And on the upstream, or day side, the solar wind compresses the magnetosphere until the magnetic pressure of the Earth's field balances the dynamic pressure of the solar wind. And typically the nose of the magnetosphere is around 60,000 kilometers above the Earth, but this distance can shrink down to 40,000 kilometers or even much less, depending on the solar wind, speed and mass. Now on the downstream side, that is the night side, the solar wind drags the Earth's magnetosphere away from the Earth, forming a magnetotail, which is over 6 million kilometers long. Within the magnetosphere, there are 2 tire-shaped regions called the Van Allen belts, which are aligned with the magnetic equator and between 1,000 and 60,000 kilometers above the Earth's surface in the equatorial plane. These belts contain energetic protons and electrons coming mainly from the solar wind. And the shape, as you can see, the shape of the Van Allen belts follows the magnetic dipole field lines, and so their high-energy particles approach much closer to the Earth at high latitudes. And they can even penetrate the atmosphere. Now, the number of particles injected into the upper atmosphere varies in response to the strength of the solar wind. Now, the inner part of the magnetosphere, where the plasma density is much higher, is called the plasmasphere. And it's shaped like a torus, also following the Earth's dipole field lines. And the field lines from the polar regions can connect to the field lines in the solar wind. And, as we've seen, this allows energetic particles to penetrate much more easily near the poles than they can over lower latitudes. You can see that here. The lower edge of the plasmasphere is called the ionosphere, It starts around 85 kilometers above the surface and extends to about 1,000 kilometers. The magnetosphere, Van Allen belts, plasmasphere and ionosphere are all composed of plasma, which interacts with the plasma in the solar wind. The layers below 85 kilometers are the lower atmosphere, which we'll look at in part 3. Now, the deflection of the solar wind around the magnetosphere involves a change in the magnetic fields in the plasma, which, as we've seen, induces electric currents according to Faraday's law. This is the diagram of the main current systems with the Earth, the small blue ball in the center. Notice the oppositely directed magnetopause and ring currents in the equatorial plane shown in red. The magnetopause current adds to the Earth's dipole field, but the ring current opposes it. And notice also the Birkeland current shown in yellow, flowing into and out of the polar regions along the field lines. It's the electrons in these currents which cause the auroras in the ionosphere at around 100 kilometers altitude. Here's another diagram from Hijima and Potemra 1976, showing spacecraft measurements of the polar Birkeland currents on the left, and a 3D visualization of a section through them on the right. The oppositely directed currents close horizontally in the polar cap regions of the ionosphere. And according to Tinsley 2008, these currents are associated with changes of up to 200,000 volts in the electrical potential of the ionosphere measured across the polar caps. The ionosphere also responds to changes in the sun's radiant output. Far UV wavelengths and X-rays maintain the ionization in the ionosphere. The amount of current flowing in the ionospheric circuits depends partly on the conductivity, and that depends on the amount of ionization. And this is one reason why variations in solar UV and the occasional X-ray outbursts are so significant. Charged particles entering from the Van Allen belts also change the conductivity. Other currents flow elsewhere in the ionosphere, including the equatorial electrojet. And finally, telluric currents in the surface of the Earth are induced in response to the various currents in the ionosphere. And these current systems respond to the cyclical changes in the solar wind parameters and other outputs. And the systems become significantly more complicated during solar eruptions. The energy in this complex series of currents is dissipated as Joule heating, particle acceleration in the auroral regions, and kinetic motions in the currents themselves. And the process of transferring energy from the incoming solar wind to the Earth's immediate environment is known as Solar Wind-Magnetosphere Coupling. And while it is well known that magnetic storms occur due to the enhanced energy transfer, exactly how this occurs is still under investigation. Hasegawa et al. 2004 suggest that establishing the mechanisms by which the solar wind enters the Earth's magnetosphere is one of the biggest goals of magnetospheric physics. The relevant parameters, or drivers, for the available input energy are the solar wind velocity, the IMF strength, and the clock angle between the direction of the IMF and the Earth's own magnetic field. A southward IMF is known to be the most geo-effective, but the precise influence of each of the drivers is a matter of considerable debate. Akosofo et al. 1981 listed 14 different formulae that have been proposed so far. Great area for research. Now, many details of the coupling mechanism are still under investigation, but one thing is certain. Again, according to Akosofo 1981, the solar wind-magnetosphere interaction is primarily electromagnetic rather than kinetic. So just to give you an idea of the magnitude of the electrical effects, here's a picture taken from NASA's Themis mission website showing the Earth connected to a 30,000 volt battery pumping a 650,000 amp current into the Arctic. So you can imagine that connected to a bar heater. So to summarize the key points of part 2. The solar wind plasma is deflected by the Earth's magnetic field, and this induces a complex system of electric currents which input energy into the magnetosphere and ionosphere. The input energy depends on the solar wind velocity, strength and direction of its magnetic field, and it's increased by the energy in solar eruptions. It's all due to the presence of solar wind plasma interacting with a plasma in the Earth's magnetosphere and ionosphere. We've also seen that the highly variable solar UV and X-ray outputs and inflowing charged particles from the Van Allen belts create more plasma in the ionosphere. This alters the current systems due to the changes in conductivity. So the ionosphere, only 85 kilometers above the Earth's surface, is connected to the Sun. So the next question is, how could these effects in the ionosphere and above alter the climate in the lower 85 kilometers of the atmosphere? The Earth's middle atmosphere is usually taken as comprising the lowest part of the ionosphere, together with the mesosphere from 85 to 45 kilometers, and the stratosphere from 45 to 12 kilometers altitude. So note that the ionosphere is already assumed to be linked to the middle atmosphere. The lower atmosphere, below 12 kilometers, is also known as the troposphere, and it's the weather and climate region. We're looking for mechanisms to link the Sun's variable output to the troposphere. There are two possible routes. The first is to look for anything penetrating down to the lower levels, such as radiation or cosmic rays, and such as can get through the ionosphere. And the second is to investigate whether the electrical effects that we've seen in the ionosphere and above could be transmitted to lower layers. Because time is limited, we'll skip the radiation effects and move straight on to cosmic rays and how they affect cloud formation. This will introduce us to the global electric circuit and the role of plasma in the lower atmosphere, which may be the most important effect of all. We know that cosmic rays are able to penetrate to low levels in the atmosphere where they cause ionization. And coronal mass ejections provide evidence of the short-term effects of a change in CR flux. Because CMEs send out plasma clouds that shield the Earth and cause the cosmic ray flux to decrease within half a day. And the largest of these Forbush decreases, as they are called, cut the cosmic ray ionization by about 10 to 15%. And Svensmark et al.'s 2009 analysis of the amount of cloud cover showed clear effects in cloud properties following the sudden decrease in cosmic ray ionization, apparently demonstrating that cosmic rays cause low-level clouds. The causative link between cosmic rays and clouds is still being debated. We know that CRs that get as far as Earth collide with molecules in the atmosphere where they create the cosmogenic radioisotopes carbon-14 and beryllium-10. And they generate a cascade of other particles which can reach very low levels, and even the ground surface. Survivors reaching the ground include neutrons and charged muons, which are mainly responsible for ionizing the air at low altitudes. After that, it gets more uncertain. There are two main theories, or possibly two different mechanisms working in parallel. Both rely on the fact that cloud droplets preferentially form around charged particles. Svensmark's ion cluster model proposes that the ions created by cosmic rays tend to cluster together. And these clusters then attract sulfuric acid and water molecules to form microaerosols. Now, if these grow large enough, then they can act as cloud condensation nuclei, or CCN, on which water droplets form. The other main model called the near cloud effect, suggests that the ions don't cluster, but they attach directly to existing aerosols in the atmosphere, which then act as CCN. So they're quite similar. It's a matter of detail. The accumulation of charged droplets means that the clouds themselves are charged. The strong electric fields at the cloud edges leads to more charging of aerosols in the vicinity, and so to further cloud growth. In the near cloud effect model, it's recognized that the creation of ions by cosmic rays and the presence of charged clouds affect the conductivity and the electrical current regime in the atmosphere. So let's look at this current regime in more detail. The surface of the Earth carries a net negative charge. Roble and Sir, 1986, give the total charge as 500,000 coulombs. The potential difference between the ionosphere and the negative surface is around 250,000 volts on average. But it varies between 150 and 600,000 volts, depending on the state of the current systems in the ionosphere. This potential difference means that the middle and lower atmospheres are like the dielectric in a capacitor. And although air is a good insulator, it's not perfect, and so the capacitor leaks. Therefore, there's an electric current between the ionosphere and the Earth, flowing in what is known as the global electric circuit. In clear skies, there's a fair weather downward current density, with a typical value of 1 to 6 picoamps per square meter, and this tends to neutralize the negative surface charge. And the circuit is completed via thundercloud regions. And following Wilson 1920, it's generally thought that the ionospheric potential difference is maintained by thunderclouds acting as generators. The fair-weather electrical current density depends on both the conductivity, which is altered by cosmic rays, and it's altered by the formation of low-level charged clouds, and it also depends on the ionospheric potential, which we've seen varies between 150 and 600 kilovolts, depending on the currents in the ionosphere. And the changes in the potential change the electric field. Now, the fair-weather electric field near the surface of the Earth varies both diurnally and seasonally. Chalmers, 1950, presents the graph shown here from data obtained at Kew. The image on the right shows the ionospheric current system on the sunward side. That's the ionospheric current system. Obviously, the current and potential above any location on the ground vary daily with the Earth's rotation under the Sun's position. The daily variations of the fine weather field have a double oscillation every 24 hours. These correlate with barometric pressure, but they're of greater magnitude. According to Chalmers, the main significance of such barometric variations lies in the alterations of the values of resistance of the lower layers of the atmosphere. But maybe Chalmers was mistaking cause and effect. All we know is that resistance and pressure are correlated. The pressure variations are also known to correlate with the fair-weather current density, and this is known as the Burns effect. Suppose the vertical electrical current density drives the associated barometric pressure changes. Then when the resistance of the lower atmosphere varies due to changes in the cosmic ray flux, we should expect to see barometric pressure changes as a result. And changes in the ionospheric potential will also change the current density, and so they too may drive the pressure changes. We saw earlier that the amount of cloud cover is also related to the vertical current density, so cloud formation may be driven by the current too. But perhaps it's not as simple as that either. The interaction between the vertical current density and the weather effects may involve a feedback loop, similar to the one we saw earlier between electromagnetic forces and movements of particles in a plasma. So changes to the global electric circuit alter the cloud cover and barometric pressure, which in turn alter the current density in the circuit by changing the conductivity or resistance. Now we do know that the sun's output triggers changes in the electrical circuit via the ionosphere and modulation of cosmic rays. Now these changes would trigger changes in the postulated feedback loop, which could then amplify the original changes by using energy from the climate systems. And this sort of feedback loop is what we should expect. Now it's been recognized that the lower atmosphere is also a plasma due to the ionization caused by cosmic rays. For example, Larkin et al. 2010 state the galactic cosmic ray flux maintains the atmosphere as a weakly conducting plasma. And they continue. As a result, variations in the GCR flux modulate the vertical current density. But I suggest that the implications may be much greater than simply modulating the vertical current density, important as that is for the amount of cloud cover and barometric pressure. Remembering what we've seen about the ways plasma in the heliosphere, magnetosphere and ionosphere interact and induce currents in adjacent regions, we should expect that the plasma in the atmosphere will behave in a similar manner, although modified by the greater density of the atmosphere. And I suggest that the implications may be much greater than simply modulating the vertical current density, important as that is for the amount of cloud cover and barometric pressure. Remembering what we've seen about the ways the plasmas in the heliosphere, magnetosphere and ionosphere interact and induce currents in adjacent regions, we should expect that the plasma in the atmosphere will behave in a similar manner, although it will be modified by the greater density of the atmosphere. This opens up a whole new set of possibilities. Now, let's conclude this talk by looking at some well-known climate phenomena and see if we recognize any plasma-like behavior. Air is a weak plasma, so are winds driven partly by electromagnetic forces acting on the charged particles, which would drag the neutral air molecules with them via viscous coupling, similar to what happens in electro-osmotic flow in a fluid, in a liquid. Now, if so, any variations in the global electric field pattern may help to generate winds. Water droplets in clouds are also charged, either positively or negatively, by up to 90 units of charge, according to Tinsley 2008. And so they too will be subject to the same electromagnetic forces permeating the weak plasma atmosphere. So are cyclones and tornadoes, partly driven by electromagnetic forces acting on the charged droplets. Global scale effects are also possible. Here's the diagram of the solar wind-magnetosphere coupling currents again. Remember the magnetopause and ring currents in the magnetic equatorial plane. These are thousands of kilometers above the surface, but others are closer in. The equatorial electrojet is an eastward current in the E region of the ionosphere, around 100 to 130 kilometers above the surface, also in the plane of the magnetic equator. The auroral ovals around the magnetic poles, shown in the third picture, are also a lower ionosphere effect, mostly occurring between 90 to 150 kilometers altitude. And during periods of increased solar activity, the auroras brighten and the ovals move towards the equator. A little lower down we find the jet stream near the level of the tropopause. In fact, there are 4 jet streams. The northern and southern hemispheres each have a strong polar jet at 7 to 12 kilometers altitude and a weaker subtropical jet at 10 to 16 kilometers. And the jet streams are assumed to be a result of fluid motions driven by pressure changes in the atmosphere related to Hadley cell circulation and modified by the Coriolis force. And I'm sure these forces do play a part. But it's not known why jets are concentrated into such narrow bands. To me, it seems as though they're behaving like the plasma in the EEJ and auroral ovals in the ionosphere. Are they primarily plasma effects, whose location is determined partly by interactions with the ionospheric current systems above? Seawater is also a good conductor of electricity, so the oceans may be involved too. It's known that El Niño and the related ENSO cycle seem to move in sync with solar activity, as do the North Atlantic Oscillation, the Atlantic Multi-Decadal Oscillation, and the Pacific Decadal Oscillation. Therefore, it's interesting to read that ENSO influences the average location of upper-level jet streams. During El Niño events, the subtropical jet stream in the southern hemisphere is displaced equatorward, or north, of its normal position. Perhaps this is putting the cart before the horse. If the latitude of the jet stream plasma is determined by solar activity in the same way as the latitude of the polar auroras, then maybe the jet streams influence the ocean cycles. Both ENSO and the NAO are said to be controlled by air pressure. Recalling that the Burns effect links barometric pressure to the strength of the fair weather electric current density, I think it's entirely possible that changes in the global electric circuit trigger the pressure changes, which in turn cause ENSO and the NAO. In the case of the PDO, certain warm and cold regions swap places in the northern Pacific Ocean and do so every 20 to 30 years. Given that seawater is a good electrical conductor, it seems highly likely that the oceans will carry currents induced in response to changes in the ionospheric circuits, similar to the telluric currents in the continents. So could these currents play a part in the swapping of warm and cold water regions with different conductivities? These are just some suggestions about well-known phenomena that we might want to revisit now that we know that the lower atmosphere is a plasma and must be linked to the events in the ionosphere and above. Having recognized the possibility, I'm sure many more examples will be found when we look. Okay, so to sum up what we've learned. At the beginning of the 20th century, scientists assumed that the Earth orbited in the vacuum of space and that it could only receive radiation from the Sun, which was emitted at a nearly constant rate. This is incorrect. We now know that the Sun is a highly variable star, that space is full of plasma which links the Sun and Earth electromagnetically, and that interaction with a variable solar wind generates huge currents and voltages in the Earth's magnetosphere and ionosphere. And we now know that the lower atmosphere is also a weak plasma due to ionization by cosmic rays, which are modulated by the Sun's variable magnetic field. We know that there's a global electric circuit linking the 150 to 600,000 volt ionosphere to the negatively charged ground. That clouds are electrified and form part of the circuit, and that cloud cover and barometric pressure vary with the current density in the circuit. There seems to be a feedback loop between the electrical effects and the weather effects, such as cloud cover and barometric pressure. We've also seen various ways in which the Sun's activity changes the ionospheric potential and the conductivity in the atmosphere, which in turn alter the current density and may trigger the feedback loop. And finally, we've recognized similarities and correlations between many climate phenomena in the lower atmosphere and oceans, and the behavior of the plasma in the ionosphere and above. So what's the conclusion? We're connected by plasma. Given all we know, I think it's undeniable that our variable Sun drives the climate. Thank you for listening.